All right. Thanks for coming. Happy Thursday. Today's planning to be pretty chill. Um, we're gonna finish the Hamiltonian part, and then any spare time left over, I'll just have for homework. You could talk with your neighbor and try and figure out some of those problems. And then next time we'll start looking at directed graphs, digraphs. Okay. Let me close it. There we go. All right, so last time, let's go all to the top here. So last time we started looking at these two fairly big problems. One of which is the explorer's problem, where the explorer wants to find out everything and see everything. And the explorer wants to find a tour that traverses each road in a map of cities exactly once and then return to the starting point. We can visit a city multiple times, and the word that we ascribe to this is Eulerian or Eulerian, where we're looking for this closed trail that is going to include every edge of the graph. So that's the explorer. And then the other side of that is the traveler. So the traveler doesn't care about what possible ways there are to get from one place to another. The traveler just cares about getting from one place to another. And so the traveler's problem is to find this tour that visits every city exactly once and return to the starting point. And it may omit roads. So some of the edges are untraveled. So the word we use for that is Hamiltonian. And what we're looking for there is a cycle that includes every vertex of a graph. So if we can find a closed trail that includes every edge, then we say, and goes back to its starting point, then we say that graph is Eulerian. If we can find a cycle that includes every vertex of the graph, then we say that graph is Hamiltonian. So we did some examples of, is this Eulerian? Is this Hamiltonian? And if it is one or the other, that means you can find a trail or a cycle that meets these definitions. If you can't find one, then it's not. So we talked about Eulerian first, where we looked at what sort of restriction can we put on graphs? What sort of definition can we have to say whether it's Eulerian or not? And the one we ended up coming up with is every vertex has to have even degree. So every vertex has to have an even number of edges incident to it. And then we ended with semi-Eulerian, which is, so normally we want to start and stop at the same vertex. But if we remove that restriction and keep the others, so every road still has to be traveled, we can say it's semi-Eulerian, where it's an open trail, so it's not a closed. It starts and ends at different places, but we still include every edge. And the theorem associated with that is it's semi-Eulerian if and only if it has exactly two vertices of odd degree. So if they're all even, then it's Eulerian. If there's exactly two odd, then it's semi-Eulerian. Otherwise, it's not. So that's where we stopped. For the packet, we went over yes or no for all of these examples. We came up with the restriction of every vertex has to have even degree. We looked at splitting it up into cycles, and then using our rule, are some of these graphs Eulerian or not? And then we looked at, with our semi-Eulerian rule, which one of these does that apply to? Okay. So now we're going to move on to Hamiltonian graphs. We're going to start looking at Hamiltonian graphs. And the guy who invented this, discovered this property, is a guy named Sir William Rowan Hamilton. So he gets this named after him. And he was looking at this game, which the drawing is in your packet, where let's say we have an icosahedron, I think, the five-sided die. And if we label each point with a letter, we can get a graph from that. Remember this polyhedral graph where we smush it all down into the plane? And that's where we get these vertices and edges. So the game that he came up with is, let's assume that like the vertices are labeled as cities. And we want to find a tour around this icosahedron and return back to where we started. If this sounds like the traveling salesman problem that we kind of looked at in the beginning, you'd be right. But the game is if I am given 5 letters to start with, I need to finish that. So if I'm given here's to get you started, finish the tour of all of them. So I've got one example that the book had where let's say we were given B, C, P, N, and M. So B, C, P, N, and M. That's our starting point. Then the game is to find how do we go around the rest of them and return back to B. So one of the possibilities is, I'll write down the letters and then we'll trace it out. So D, F, K, L, T, S, R, Q, Z, X, W, V, J, H, G, back to B. Okay, so we go to D, F, and then K, then L, T, up to S, across to R, down to Q and Z, and then X, W, down to V. We don't care about the edge between N and S or the edge between R and W. We only care about visiting each vertex. And then, so we're at V, and then J, H, and G, and we're back to B. Right? So we're trying to go around the world. And there's multiple options here. So the book gives another option, but this path is not necessarily unique. We're just trying to find a way. Okay, so this is the problem 6 on the packet for how many Hamiltonian cycles. So the cycle that I just found that goes from B all the way around and back to B, that's a Hamiltonian cycle. So try it with JVT SR and try and figure out how many there are. So first find one and then try and find another. Did we find one yet? Yeah. Someone want to give me? Here, let me erase this. Someone want to give me theirs? Go for it.
I got, so the first word, JVTSR.
JV.
WXCQ.
Wait, hold on. Sorry. JVTSR. Okay. W. G. H. Yeah. And then back to J. Yeah. Cool. Anybody else get a different one? Yeah. Hold on. Let me actually. JVSR. WX. HG. Yeah. Awesome. Anybody find another one? Cool. So what the book says, first of all, do we have an idea? Are there any more? No. Yeah. So what the book says, the answer here is 2. And we found both of them. Okay. Now we've also got problem 7. Which is slightly different, to find a path. So start with B, C, D, end with T, and with that same restriction of each vertex once. There's only one, so hopefully we should all get the same answer. find it? Maybe? What did you get?
So BCD,
Mm-hmm.
then FGH, XZQ, PNM, LKJ, BWR, and ST.
Yes, then go all the way around. Yeah. Did everybody get that? Anybody get something different? Cool. All right, so that's the game. Just to give you practice finding either a Hamiltonian path or a Hamiltonian cycle. Okay. So then there's some more packet problems. I will note that so there's not so much of like lecture component for Hamiltonians. It's mostly trying it out, packet problems, because it's an open area. So whereas for Eulerian graphs, we have like a really handy theorem to say even degree Hamiltonian, or sorry, even degree Eulerian. We don't have that for Hamiltonian. It's an open problem to try and find a restrictive definition or a theorem that says for sure this is Hamiltonian. It's hard. And the reason that it's hard, one of the things that if you take like if you were to go on and take like graduate classes in computer science, you would talk about something called NP completeness, which are basically really hard problems that we can like definitively prove this is really hard and we don't know if we can complete it in what's called polynomial time. Otherwise, it's much harder than that. So the traveling salesman problem, which is kind of what Hamiltonian is, traveling salesman is NP complete, which means it's really hard. And so that's kind of why if you do find a restriction for Hamiltonian cycles, then you like win your PhD and you win like, what was it, like Millennium Prize, $1 million type thing. So yeah. So what we've got now is mostly practice. Let's try splitting up into group because we've just got like practice problems left for the most part. So let's do 8 and 9. Let's have this half do 8A and this half do 8B. Just like talk to your neighbor and reason it out. You may have this half may have to scrunch together. Go talk to each other. Okay, I hear a consensus over here. Is a tree Hamiltonian? No? Is there a kind of tree that is Hamiltonian? What? Path tree? Um, right, because we can't get back to the start. This would be, so we've got a definition for semi-Hamiltonian, which is like the same kind of thing where we start and end in different places. So a tree, I guess, would be semi-Hamiltonian, but there is a tree which is trivially Hamiltonian. Does anybody know what it is? Yeah? Yeah, just a vertex. There's no edges. So trivially, it is Hamiltonian. I didn't give you guys a lot of time to chat. Do you want a few more seconds? It is? Okay, now let's spend 30 seconds drawing K4 so I can spend 5 seconds talking about it. Or K44. 4, 1, 2, 3, 4. So why is it Hamiltonian?
Exactly way to.
Yeah. Yeah. Great. All right. I will say, actually, no. So this is our definition of semi-Hamiltonian, which is where we find a path instead of a cycle. Quick question for you. If we have a graph that's Hamiltonian, I don't know, let's say like the house. So like a cycle is Hamiltonian. If we have a graph that is Hamiltonian and we add an edge, is it still Hamiltonian? Yeah. How come? Yeah. Right. Extra edges don't matter. These are the kind of things that graph theorists like to think about of if we add one more, does this property still hold? If we remove this one thing, does that change anything? Okay. Okay, so we did problem 8. Problem 9. So maybe we split into smaller groups. For you to like work with your neighbor on problem 9. So maybe you two, then row by row of, I want to know if a bipartite graph with an odd number of vertices, so maybe 2, 1 or something like that, just an odd number of vertices is not Hamiltonian. And then use that to show that the example here isn't either. Go for it. Right, do we have a consensus? Ideas for how to prove A? Sure.
Have an odd number of vertices, one side must be bigger than the other.
Mm-hmm.
No matter what side you put on, once you reach that's the end of that side. I think there aren't enough vertices on the other.
Yeah, so the nature of because to find the cycle, we're gonna alternate between A and B. And eventually we're gonna run out of vertices in one of them. So when we alternate between A and B, we're gonna run out of vertices, so we're gonna have to repeat something. That makes sense to me. Anybody else have another way of explaining it? Another way of reasoning about it? Okay. So why is this one not Hamiltonian? Someone from this side of the room. Any ideas? So we use this, if we just reasoned that we can't use or like a bipartite graph with odd number of vertices isn't Hamiltonian, then the solution here is to what? Show it's bipartite with a non-number of vertices. That would give us our solution. So we can color all the vertices. So if I put a circle around, so remember we colored with like a circle, an open circle or a filled in circle. So maybe if I put a circle around one of them, so this one, but not this one, but not this one, but not that one. And so forth. So I think I got all of them. So this shows that since we can color it this way, it shows it's bipartite. So bipartite check. And now the question is, does it have an odd number of vertices? Which we can go and count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So since both these things are true, and we just proved A, great. we can say it's not Hamiltonian. So we have to do a little bit more work for a graph. So if we can find a Hamiltonian path, then we did it. The graph's Hamiltonian. If we can't find a Hamiltonian path, we need to prove it in some way. This is one thing where, oh, I didn't find one, therefore it's not Hamiltonian. That logic doesn't hold here. So we need to use the results of this lemma that we just proved to show that for this graph. Any questions? Okay. Let's look at problem 11. So I skipped problem 10. That was a theorem that it gives like it's a simple connected graph and it looks at the degrees. If you're interested in that, I would refer you to the book. I will note that the guy who wrote that theorem was, I pulled up his Wikipedia page earlier. He was this Norwegian mathematician, but he also, he was the advisor for some famous doctoral students, one of which is Grace Hopper, who there's the Grace Hopper Conference for Women in Computer Science that it's named after, and so she did a lot of really cool things. So I thought that was interesting that I would bring it up, but we won't talk about his theorem. So we skipped problem 10, and now that we know semi-Hamiltonian, again in your groups, try and figure out which of these is semi-Hamiltonian, and I would like to know the path if it is. Yeah.
Was the theorem that is that if like a simple graph has something degrees for at least both semi.
Simple graph that has the same degrees for it to be Hamiltonian. Let me review the actual theorem. Yeah, so the theorem looks at like if you add 2 degrees and it's greater than or equal to the number of vertices for any pair, then it's Hamiltonian. Yeah, and so the tricky part with that, the reason why it's not like such a simple definition is that we're looking at any pair. So not just like a pair, but any pair. Yeah, no. One or the other or not. All right. Do we have an answer for A? Someone tell me their answer. Anybody? Yeah. Great. And since we proved in the last problem that this graph's got an odd number, we know that it can't be Hamiltonian in general. What about B? Someone else?
That it was more fun. Because C, B, B, A, C, is that B second?
Yep. What about C? Someone else? Yeah.
Hamiltonian, you start on W, so you go from
W
Y, X, B, C, back to W.
back to W. Yeah. Great. Awesome. So that's the end of the packet. And my plan for the rest of the class is if you would like, I'll give you time to maybe still talk with your partner and think through the homework if you've still got work to do on that. Do you want to keep the packet until the homework's due? Would that be more helpful? Okay, so I'll just make the packet and the homework due the same day. But yeah, the rest of the time, just work on the homework, talk it through with your neighbor. And use this time to your benefit.